Hello everyone. In this lecture of the Stochastic Processes course, we will be focusing on digital stochastic processes. We will start with the special case of binary stochastic processes, and then we will generalize that to the M-ary stochastic processes. Let's first start with understanding what is meant by binary stochastic processes. A binary stochastic process is a process in which the amplitude or the value of the process has only two values. These two values might represent bit 0 and bit 1 as in case of binary data. However, these two amplitudes are not necessarily 0 voltage and 1 voltage. They are rather two amplitudes that represent binary bit 0 and binary bit 1. In order to have some examples of signals that can be used to represent zeros and ones, let's talk for a while about what we call line codes. Line codes are used for the electrical representation of binary data stream. So they are signals that map to binary bits 0 and binary bit 1. And we have a number of these representations. For example, we have what we call unipolar non-return to zero signaling. We have polar non-return to zero signaling. We have unipolar return to zero signaling, bipolar return to zero signaling or alternate mark inversion, and finally split phase signaling or the Manchester code. In the following, we will try to understand each of these representations and how they are used to represent bits 1s and 0. Let's start with this example in which we have binary data of 011010001. For this first representation, we have bit 0 is represented as 0 voltage, while bit 1 is represented as 1 voltage. And of course, since each bit has a specific duration, we call it TB, the duration of each bit. As we can see in this representation, that the voltage used to represent bit 0 or bit 1 is used for the whole duration of the bit, for the whole TB. That's why we call this non-return to zero signaling, which means that, for example, if we are representing bit 1 with A voltages, we keep representing the bit with A voltage for the whole TB duration. We do not represent it for example, half TB and then return it to 0. That would be return to 0 signaling. However, in return to 0 signaling, we keep the voltage at its specific level for the whole duration of the bit. In this example, we are using single polarity. We represent bit 1 with A voltages, positive A voltages, while bit 0 is represented by 0 voltages. That's why we call it unipolar. So we have unipolar non-return to zero signaling. For the next representation, as you can see, we are representing bit 0 with negative A volts, while bit 1 we represented with positive A volts. So in this case, we have polar representation, which means we use both polarities, positive and negative signals. So it is as if we are representing bit 1 with a rectangular pulse, which has an amplitude of positive A volts and duration of TB, while bit 0 is represented by a rectangular pulse, which has a magnitude of negative A volts and also a duration TB. So we have two polarities, so it's polar representation. And as we said earlier, since we keep the same voltage level for the whole duration of the bit, for the whole TB, we call it non-return to zero. So while the first one is unipolar non-return to zero signaling, the second one is polar non-return to zero signaling. For the next representation, we will see the return to zero signaling. The first one here, as we can see, we represent bit 0 with 0 voltage for the whole TB duration. So that is 0 voltage. While for bit 1, we represented by A volts for some duration of the bit, and then return to the 0 voltage for the remaining interval of the bit duration. Please note here that this whole duration is TB. So we are not keeping the A volts representation of the bit 1 for the whole bit duration. We rather return to 0 within the bit duration. So in this case, we have return to 0 signaling. Of course, return to 0 signaling helps us save more power than the non-return to 0 signaling. And if we want to ask whether we have here polar or unipolar representation, first, we note that bit 0 is always represented by 0 volts, like bit 0 in here, bit 0 in here, bit 0 in here, and so on. However, whether this is unipolar or something else, we might notice here that for bit 1, it is sometimes represented by a return to 0 pulse, which has an amplitude of positive A, like the first one we have in the stream, while the next bit 1 is represented by a negative voltage, which is negative A volts in this case, and again we return to 0. So in this example, we have what we call bipolar representation. More specifically, it's bipolar return to 0 signaling, in which we represent bit 0 with 0 volts, while bit 1 is alternatively represented by positive A and then negative A. So for the first or the odd ones, we represent them with positive A volts, while for the even ones, we represent them by negative 1 volts. Another name for this type of signaling, we call it alternate mark inversion. So mark represents bit 1, and we alternatively invert its representation between positive A and negative A. Again, notice here that each bit 1 is either positive A volts and then it returns to 0, or it's negative A volts and then it returns to 0. However, if the last bit 1 was positive, then the next bit 1 will be represented as negative A volts and vice versa. So this is alternate mark inversion. We might be interested in using this type of representation if we want, for example, have an average of the signal close to 0, because all the 0 bits are represented by 0 volts, so its DC is 0. And then if we have an even number of ones, so half of them will be represented by positive A volts, while half of them will be represented by negative A volts, and then our DC of such signal is 0. However, if we have an odd number of ones, so we will have a DC which either close to 0 with a positive value or close to 0 with a negative value, because in this case we will have an extra 1 bit with either positive A volts or negative A volts. So this is what we call bipolar return to 0 or alternate mark inversion. Of course, if we have unipolar return to 0 signaling, that means that 0 bit is represented by 0 volts everywhere in the stream, and 1 bits are represented by positive A for some duration, and then we return to 0 for every bit 1 in the whole stream. So this is unipolar return to 0 representation. However, what we can see in this figure is bipolar return to 0 signaling. The next representation, let's see how it represents bits 0s and bit 1. For the first TB, which resembles bit 0, the signal has an amplitude of negative A volts for half the bit duration, and then it rises to positive A volts for the other half of the TB duration. And for bit 1, for the next TB, it is represented by positive A volts for half the duration, and then negative A volts for the remaining half of the bit duration. So if we draw them right here, bit 1 is represented by half positive A volts, and then the remaining half of the bit duration is represented by negative A volts. So we have here positive A and negative A, while this whole duration is TB. And for bit 0, it is represented by the inverse, which is negative A volts for the first half of the bit duration, and then positive A volts for the second half of the bit duration. So this type of representation is called the split phase signaling or split phase representation, because each bit is split into two durations which have a phase change of 180 degrees, or the first half is positive and the second half is negative in case of bit 1, and vice versa in case of bit 0. Also, this representation is called Manchester code, and one of the main systems that use such a representation of ones and zeros is in networks where we have an Ethernet signaling. The signals are represented, or the bits are represented by Manchester codes. Of course, one of the main advantages of such code is that the average or the DC of each bit individually is 0, which means irrespective of the data stream, whether it has more ones than zeros or the other way around, or whether it has an odd number of ones or an even number of ones, always the DC of the whole signal will be equal to 0, because the DC of each bit individually is equal to 0. So sometimes this is suitable for some applications. Now that we know the different representations of binary data, streams of ones and zeros, let's analyze them as random processes to find their statistical descriptions, to find their mean, their autocorrelation function, and their power spectral density to have an estimate of their frequency content. Let's start with polar non-return to zero signaling, in which bit 1 is represented by a positive pulse and bit 0 is represented by a negative pulse. That is the meaning of being polar. And for non-return to zero signaling, our pulse is a rectangular pulse with an amplitude of 1 and duration of TB. That is the whole bit duration. So this is our pulse B of t. And whenever we have bit 1 in our data stream, it is represented by positive B of t or A B of t, because we said that in polar non-return to zero signaling, we represent bit 1 with A volts, where that A can be any value. And bit 0 is represented by the polar representation of this pulse, or with negative A multiplied by B of t. Of course, this signal can be expressed as a time domain function as a rectangular function with width TB. And since our conventional terminology of rectangular function is a rectangular function centered around the origin, however, this one is not centered around the origin. It is rather shifted from the origin with TB over 2. So we have such term here which indicates this time shift. And the whole stream of ones and zeros is represented by a sequence of pulses, and these pulses are either positive or negative according to the corresponding bit. And hence our signal, which is in general a random signal, because we don't know we don't know deterministically what is the sequence of ones and zeros. It is a random sequence. So we have summation of pulses B of t shifted by integer multiples of TB. So this represents the sequence of bits, ones and zeros. Moreover, in order to keep the representation generic, we don't know whether the origin starts or whether the origin exists at the beginning of one bit or in the middle of one bit. So we represent that randomness by the factor alpha, where in general we assume that the first pulse is equally likely to occur at any time instant within a window of TB from 0 to TB. So in this case, our alpha is a random variable which represents the place of the origin within the first pulse, and each of our pulses is amplitude scaled with a random variable an, where this an is either positive a if we have bit 1 and negative a if we have bit 0. So this is the random process that can be used to describe polar non-return to zero signaling. As we can see here, we have a stream of pulses. These pulses alternate between positive A and negative A, and such alternation occurs at a rate of TB. There are no transitions except after TB. This is the bit duration because we have non-return to zero signaling. However, the origin arbitrarily can fall within any bit duration. And if we focus on one of the pulses like here, we can see that we have some transition here from negative A volts to positive A volts, and again here from positive A volts to negative A volts, as if we have bit 0 here, bit 1 here, and bit 0 here. And again, our origin can be arbitrarily located anywhere within the bit duration. And what we need to do right now is to calculate the average of this random process, its autocorrelation function, and its power spectral density. In order to understand this more, let's first draw the ensemble of this random process. If we draw the ensemble of this random process, let's draw some sample functions of such random process. Let's assume this is the origin. So we can have a stream, for example, starting right here with bit 1, followed by bit 0, followed by another bit 0, followed by bit 1, and then bit 0, then another 0, then another 0, and 1, 1, 1, 0. So this is one sample function. Another sample function can be starting like here with bit 0, followed by bit 1, another bit 1, another 0, another bit 1, 0, 0, 1, 0, 1, 0, for example. And also we can have another stream which starts right here with bit 1, followed by bit 0, another bit 1, 0, 0, 0, 1, 1. So as we can see from these sample functions, the randomness exists in terms of two parameters. The first parameter is an, the amplitudes of the signal, which can alternate between positive A and negative A, or can arbitrarily be either positive A or negative A. And also another source of randomness is the starting point of the binary stream, which determines whether the origin falls at the beginning of one bit, at the end of one bit, or within any time instant of TB duration within a bit. In order to calculate the autocorrelation function Rx of tau of this random process for this polar non-return to zero signaling, as we used to, we take two samples arbitrarily at time t and time t plus tau, so they have time difference of tau, and then we calculate the average of the product of these two random samples. So the autocorrelation is the average of x1 times x2, where again x1 is the value of the random process at time t1 and x2 is the value of the random process at time t2. Because this problem is a binary random process in which the amplitude of the random process or the random signal is either positive A or negative A, hence our calculation of the autocorrelation function will be similar to discrete random process in which we have only 4 possibilities of the pair of x1 and x2. So we have summation over all the values of x1, summation over all the values of x2 for x1 times x2 times their joint probability. However, x1 is either positive or negative A and x2 is either positive or negative A, and hence this double summation is summation of 4 terms, and these 4 terms are either both x1 and x2 have values positive A, and in this case this term will be multiplied by the joint probability that both the first and the second sample, again which are arbitrarily taken at times t1 and t2, or t and t plus tau will be A and A, or one of them is negative A and the second A, in which case this product is multiplied by the joint probability of negative A and A, and similarly the second term and the third term, and finally the fourth term, which in which these 4 terms take all the 4 possibilities of the combinations of x1 and x2. Of course, in continuous random process or in analog random process in which the amplitude can take any value from an infinite set of values, our calculation of the autocorrelation function was via integration. However, because of the nature of this problem in which the amplitudes are taken from finite set of amplitudes, in this case more specifically there are 2 amplitudes, a binary case, hence the autocorrelation is calculated simply by summation of the corresponding terms. So by simplification that would be A squared multiplied by the summation of these 4 joint probability terms, and from the symmetry of the problem we can deduce that the joint probability of A and A is similar to the joint probability of A and the negative A. So that is the probability that the first sample is A and the second sample is A is similar to that the first sample is negative A as well as the second sample is negative A. Similarly, the probability of negative A and A is equal to the probability of A and negative A. So we have 2 taken as a common factor, and we have these 2 probability terms or these 2 joint probability terms. If we want to better understand it, let's assume that we have 2 sample functions. For example, the first sample function has positive A, negative A, negative A, negative A, and positive A, and so on. And the second sample function is arbitrarily different. And we are taking 2 sample functions, 2 samples, one at time t and the other at time t plus tau. So the 2 samples for the first sample function can be, in this example, positive A and the negative A, while in the second sample function it is negative A and positive A, and each one of them is multiplied by its joint probability. Moreover, these joint probabilities, probability of A and A and the probability of A and negative A, can be calculated using Bayes' rule, where probability of A and A, the probability that x1 is equal to A and x2 is equal to A, is equal to the probability that the first one is A or the second one is A, given that the first one is A times the probability that x1 is equal to A. So again, this is x2 equal A given that x1 equal A. Similarly, probability of A and the negative A is equal to the probability that the second sample is negative A given the first is A times the probability that the first is A. So in this case, we can take the probability of A as a common factor outside, and we have the joint probability of A given A minus probability of negative A given A. Of course, you can notice that these two probabilities, these two conditional probabilities, are complementary, because one of them is the probability of A given a certain condition, while the other is the complementary event, which is probability of negative A given the same condition. So we can say that probability of A given A is equals to 1 minus probability of negative A given A, and with substitution we can get between the brackets we have 1 minus twice probability of negative A and A, and if we assume that our binary stream is equiprobable, which means that the probability of having 0 is equal to the probability of having 1 equals half each of them, then the probability of having any amplitude A is equal to half. So simply, after simplification, we are left with that the autocorrelation function is equal to A squared times the term 1 minus twice probability of negative A given A. So the question now is how to calculate this joint probability, the probability of negative A given A. The tricky part here is that this conditional probability depends on tau. It depends on how far are the two samples taken at time t and the time t plus tau from each other. So that depends on the value of tau itself. So for the first case, if tau is larger than TB, which means that both samples are taken at two different bits, because if tau is larger than TB, that means that definitely the first sample and the second sample fall within two different bits. So in this case, the probability of negative A given A represents the probability that the second sample or the second bit is represented by negative A given that the first is represented by A. Or in other words, it is the probability that the second bit is 0 given that the first bit is 1. And since they are two different bits far from each other, separated by more than TB, that means that there is no dependence between them. Of course, that will be described that the stream of bits is characterized by the fact that individual bits are independent of each other. However, what assures us this independence here is that tau is larger than TB. So both values are taken at different bits, which means they are independent from each other. So as we know from such independence, if the two joint random variables are independent, then the conditional probability is equal to the marginal probability. So it is equal to the probability that the second one is negative A, which is half as we calculated before. So if the two samples are separated by tau larger than TB, that means that the conditional probability equals to the marginal probability equals to half in this case. On the other hand, if tau is less than TB, then we have possibilities here. If tau is less than TB, that means that the two samples, x1 and x2, are separated by less than the bit duration. So we might have both samples falling within the same bit if there is no transition within the tau. However, it might happen that we have a situation in which the two samples are separated by less than TB, yet there is a transition in between. Let's draw both cases. Let's assume that these are the two samples, T and the T plus tau, or these are the two time instants. We might have a scenario like this, where this is one bit and this is the other bit, or we might have a scenario like this, where both samples are taken in the same bit. So in order to calculate the joint or the marginal probability in this case, we need to consider both scenarios. So let's start with the first scenario, or let's start with the second scenario first. In the second scenario, in which both samples fall within the same bit. In this case, what is the probability that the second is negative A while the first is A? Of course, in this case, the probability is equal to 0, because since they fall, the two samples fall within the same bit, they cannot be different from each other. While for this case, the probability of having negative A given A, so this is the probability that the second is negative A given that the positive is A. And since they are two different bits, they are independent. They are successive bits, however, they are still independent. And similar to the scenario above, it is equal to half. So the question now is how to combine both probabilities. So the overall probability of negative A given that the first is A, is equal to half times the probability of having a transition plus 0 times the probability of having no transition. Of course, this term is equal to 0 irrespective of the probability of transition. So the question now is, what is the probability of having a transition, which means transition from one bit to another, whether transition from bit 0 to bit 1 or from bit 1 to bit 0, within a duration of tau. If you recall, this depends on the origin. Where is the origin located with respect to the bit representation? So that depends on the random variable alpha. So the probability of having a transition within a bit duration of TB, let's recall what was the probability distribution of alpha. Alpha was distributed between 0 and the TB, and it was uniformly distributed, so it has a representation, a probability of density function of 1 over TB. So the probability of having a transition is equal to the probability that alpha is less than or equal tau, such that we have a transition within the bit duration. So that is simply tau over TB. So this is the probability of transition, which means that the conditional probability of negative A given A is equal to half times tau over TB. So in order to proceed, we have to consider both cases, the case when tau is larger than TB and the case when tau is less than TB. Substituting with what we obtained, we can say that for tau larger than TB, the autocorrelation function is equal to A squared times 1 minus 2 multiplied by half, which is equal to 0, while for tau less than TB, the autocorrelation is equal to A squared times 1 minus twice multiplied by half tau over TB, and of course we can cancel this, and we have the autocorrelation for tau less than TB is equal to A squared times 1 minus tau over TB. Recall that the autocorrelation function is an even function, so this equation is valid for positive tau, and its even version is valid for negative tau, and hence we have the autocorrelation function represented by a squared times 1 minus the absolute of tau over tb in case tau is in absolute less than tb and 0 otherwise. And if we plot such autocorrelation function, we have this rectangular shape. Of course, it has all the properties that we discussed before about autocorrelation function. It is an even function. It is a real function. Its peak is at tau equal to 0, and it is a non-increasing function. In order to calculate the power spectral density of the random process of polar non-return to zero signaling, we just calculate the Fourier transform of the autocorrelation function. And as we know from the Fourier transform pairs, a triangular function in time domain has a frequency domain representation by a sinc squared function. So we have a squared tb sinc squared of omega tb over 2 pi. And if we plot the autocorrelation function side by side with the power spectral density, we have the sinc square representation of the power spectral density, where when plotted versus omega in radians per second, we have the first zero crossing at 2 pi over tb, the second at double this value 4 pi over tb, and so on. While when plotted versus the frequency f in hertz, our zero crossings are at multiples of rb, where rb is equal to 1 over tb. And it is meaningful to use rb here because it represents the bit rate or the speed of representation of ones and zeros. If we apply the same procedure for unipolar non-return to zero signaling, we can exactly follow the same steps with only one exception, is that bit 0 is represented by, rather than an amplitude of negative A volts, it is represented by an amplitude of 0 volts, which means that some terms of the autocorrelation functions that we calculated will reduce to 0. So following the same procedure, we can find that for tau less than tb, the autocorrelation function is calculated as shown, while for tau larger than tb, the autocorrelation function is not 0, it is rather 1 over 4 a squared. So again, if we plot this autocorrelation function, we can see that it can be plotted as a function of tau as follows. It has a triangular shape up until tb, and then it becomes constant at a level of 1 over 4 a squared, and of course the peak here is half a squared. One way of reaching such expression is relating the unipolar non-return to zero signaling to the polar non-return to zero signaling, because with simple manipulation you can consider that unipolar non-return to zero signaling is similar to polar non-return to zero signaling, amplitude scaled by a factor of half, and then amplitude shifted by a factor of a over 2, such that instead of being limited between negative a and a, it is now limited between 0 and a. So you can think of it in two different ways. One, a systematic way, exactly as we concluded or as we derived the autocorrelation function of polar non-return to zero signaling, or just using manipulation as we used to do with signal analysis. Of course, for the power spectral density, it can be obtained by the Fourier transform of this signal, and the Fourier transform of this signal can be calculated also as follows. You can assume that this autocorrelation is the summation of two signals, a DC signal at an amplitude of quarter a squared, and this DC signal has a Fourier transform of a delta function. So it is 1 over 4 a squared delta of omega, And the other function is the triangular function, which as before has a Fourier transform of sinc squared as represented here. Next, let's focus on M-ary stochastic processes. In M-ary stochastic processes or M-ary random processes, we might have a pulse of any arbitrary shape like P of t. It is not necessarily a rectangular pulse as we discussed in the previous examples. And also its magnitude is not necessarily one of two magnitudes as in the binary case, whether these two magnitudes are positive and negative A or 0 and positive A. Rather, the pulse might have one of m different amplitudes. It is still a discrete case in which, or a digital case in which the amplitudes of the pulse or the scale of the pulse, the weight of the pulse, is taken from a set of discrete random variable. However, it is not necessarily a binary random variable. Instead, it might have m values, in which case we call it M-ary variable, and the result is an M-ary random process. So we have again a stream of pulses of an arbitrary shape P of t for a defined for a duration of Tb, and these pulses are time shifted from each other by integer multiples of Tb. They arbitrarily start at alpha seconds from the origin. This is a random variable, and they arbitrarily weighted or scaled by amplitudes ak, where a is taken from a set of m distinct values or m possible values of the amplitude. Of course, this case is a generic case compared to the binary case that we discussed before. For example, if we have polar non-return to zero signaling, so we have this M-ary random process in which AK is taken from the set of positive A and the negative A, and in which P of t as a pulse is taken as this rectangular pulse of amplitude A and duration Tb. Also, if we want to apply Manchester code for this M-ary random process, so again we have AK taken from the possible amplitudes positive and negative A, while the pulse P of t can be now represented as +1 for the half of the duration and then -1 for the other half of the duration. So if we can in general find the statistical behavior, the mean, the autocorrelation function, and the power spectral density of this M-ary random process, then we can use it to obtain the autocorrelation function and the power spectral density of all the signaling techniques that we discussed earlier, or the different representations of binary streams of data. So first, it can be shown that the average of an M-ary random process, which we call y of t here, is the expected value of AK, the different amplitudes, multiplied by the time average of the pulse P of t, or calculated as integral of Bm dm divided by Tb. Recall that y of t was equal to the summation of AK for pulse P of t shifted by k multiples of Tb. So this is the kth pulse, and it has an overall time shift of alpha from the origin. So the expected value of this pulse is the summation of the expected value of these values. So the expected value of AK times P of t minus KTP minus alpha. And since the amplitudes AK are independent of the time shift alpha, hence we might resemble this as expected value of random variable 1 times random variable 2, and since they are independent, then this joint expectation is equal to the product of the individual expectations. So we have that will be equal to summation of expected value of AK, and of course this summation is over K. It is summation for all the successive bits times the expected value of P of t minus KTP minus alpha. So in order to calculate the expected value of AK, we need of course to know the distribution of AK and the possible values of AK. However, since the amplitudes AK are taken from the same set, irrespective which symbol are we talking about, irrespective the value of K, then this expectation is independent of K. So it can be taken outside the summation. Then we are left with the expected value of the pulse taken as summation over K. Of course, this summation is, or the expectation is again independent of K, since all the pulses are similar. After we have excluded the amplitude AK, all the pulses representing the K symbol are all similar. So the expectation is also constant and it can be taken outside the the summation without loss of generality. And this expectation is over the random variable alpha. And since alpha is uniformly distributed, it has a probability density function of 1 over TB. So this is the term that is taken outside here. And we are left with the summation, the integration or the expectation of the pulse P of t minus KTB minus alpha, which can be simplified as the integral of the pulse P of M dm, where M is an arbitrary parameter here to indicate the integration of the pulse of P of t over the whole duration. Since P of t has a duration from 0 to 2 to TB, hence this integration here can be reduced to integration from 0 to TB, or without loss of generality we can keep it as an integral from negative infinity to infinity. Using similar approach, it can be shown that the autocorrelation function is represented by this form. It is 1 over TB multiplied by the summation over n, where n is an integer value from negative infinity to infinity, for r of n times the time function phi sub p of tau minus n TB, where r of n is defined as the autocorrelation of the amplitudes AK. So r of n is the expected value of AK times AK plus n. Note that the amplitudes AK are the M-ary amplitudes of the pulses, so they have finite set of values and their expectation can be calculated by summation. And since we are multiplying the amplitude at time instant K times the amplitude at time instant K plus N, and we are taking the average, so it is equivalent to that is the definition of the autocorrelation function at time difference N. So R of N can be calculated for the amplitude scales alpha AK irrespective the pulse shape, while phi p it represents the time autocorrelation of the pulse p of t, so it is the integral of p of t times p of t plus tau dt. So this resembles the time autocorrelation of the pulse. Of course, note that the pulse itself is a deterministic function, so its statistical average will be the same as its time average because it's a deterministic function. Again, the randomness in the pulse, it's in the M-ary train of pulses, is in the amplitudes of the pulses and their time shift. It is not in the shape of the pulse itself. And of course, the frequency representation of this phi p of tau is the absolute squared of p of omega, where p of omega is the Fourier transform of p of t. Because again, this time autocorrelation function can be seen as the convolution between the pulse b of t and its time reversal version b of negative t. And hence, the Fourier transform of such convolution is the product of the Fourier transforms of p of t and p of negative t, which is absolute of p of omega squared. Of course, this can be derived from the definition of the autocorrelation function Ry of tau, and that will be left for you as an exercise to do. However, it is more important here to understand how to use this result. So this result is very powerful because it allows us to calculate the autocorrelation function of any M-ary random process by splitting the problem into two simpler problems. One of them is related to the M-ary amplitudes themselves, so we can calculate the autocorrelation function of the amplitudes AK irrespective of the pulse shape. So whether we have two amplitudes or M amplitudes, whether these amplitudes are unipolar or polar or have any other forms, that can be calculated irrespective of the pulse shape itself. And the second part of the problem is to calculate phi p of tau, or the time autocorrelation of the pulse shape, which can be calculated for the pulse irrespective the amplitudes AK. So whether the pulse is a rectangular pulse, a full rectangular pulse, or a return to zero rectangular pulse, or a split phase rectangular pulse, such as in the Manchester code, or any other pulse, for example, a triangular pulse or any general pulse, it can be calculated as, or can be used to calculate this time autocorrelation function irrespective of the amplitudes AK. And then substituting in this expression, we get the overall autocorrelation function. And in order to get the power spectral density, it is the Fourier transform of the autocorrelation function. And this Fourier transform can be calculated for this summation, which is again 1 over Tb is a constant. This summation of Rn, we can find it here because the Fourier transform is a linear process. So the Fourier transform of summation of weighted function is the summation of their weighted Fourier transforms. And of course, R of n is not a time function, it is just a scale while we are calculating the autocorrelation, while we are calculating the Fourier transform, and we are left only with the Fourier transform of this function. The Fourier transform of this function, this is a time shifted function, so its Fourier transform is the Fourier transform of the basic function, which is phi of tau, and here we calculated it as p of omega, and multiplied by a phase shift corresponding to this time shift, and this phase shift is represented by this exponential term. Only this exponential term is function of n, so it is kept inside the summation, while p of omega itself can be taken outside. Again, the strength of this result is that the power spectral density of any M-ary random process can be calculated as follows. We first need to find the time, the frequency representation of the pulse shape. This is p of omega. and then obtaining the absolute squared of this frequency representation is straightforward. And then the second step is to find R of n, which is again a simple autocorrelation function of a discrete random variable, ak, and substitute in this summation. So for any pulse shape B of omega, any polar random process will have the same second part. So you can use this result to calculate, for example, unipolar non-return to zero signaling, the power spectral density of such signaling, and then you can use the same result to find the power spectral density of unipolar return to zero signal. All what you need to change is to change P of omega, or polar Manchester coding. So you use the same result, but you change the power spectral density to P, the power spectral density of the split phase signaling, and so on. So this result is very powerful, that it can split the problem of calculating the autocorrelation function and the power spectral density of any M-ary random process into two parts. One part is dependent only on the amplitudes, and this is a discrete random variable which can be easily calculated, and the second part dependent on the pulse shape B of t, which is a deterministic function, and we can easily find its time and frequency representations using the Fourier transform analysis. So you can try using this generic approach to calculate again the autocorrelation and power spectral density of polar non-return to zero signaling for on-off signaling, or this is another name for the unipolar non-return to zero signaling, for bipolar non-return to zero signaling, and for Manchester signaling. So in brief, in this lecture, we started with the binary random process, and we found that calculation of the autocorrelation function and the power spectral density follows the same approaches that we used before for continuous random processes. And then we generalized the case of binary random process to M-ary random process, and we reached a generic formula for the autocorrelation and power spectral density that can be used to calculate the statistical and spectral behavior of any M-ary random process.